This video will look at the introduction to a new unit on structure and materials. In this unit, we're going to examine the science of mechanics. Mechanics is an area of physics that involves the study of forces and their effect on objects. It's broken into two sub-areas called statics and dynamics. Statics is the study of objects that are at rest and the study of what to do to keep those objects at rest. And dynamics is the study of objects that are in motion. This unit is primarily going to look at statics and quantitative values that are useful in that area. These will eventually build up the truss and bridge analysis. We're very interested in statics mainly because when we have a structure, such as a building or a bridge, we have the tendency to like it to stay where it is and to stay upright, and to keep the people inside of it safe without collapsing on them, or for a bridge, we don't want bridges to collapse under cars, under a load. So statics is a rather important area in structural engineering, civil engineering, mechanical engineering. So we're going to examine the following. We're going to look at some of these properties are centroids. That will be the topic of this lesson. Factors that affect beam elasticity, how much bend and flex a beam can take. We'll look at free body diagrams, which are also force diagrams, along with vector addition. We'll look at something called moments, which are really just torques and their calculations, and all those features built into a larger system with truss analysis at the end of the unit, and eventually bridge design. We're going to start by looking at centroids. Centroids, as a general concept, are our way of identifying the middle of something, looking for the center. So as we look at some centroid principles, first of all, it's the object's center of gravity, or the center of mass. It's labeled with this symbol, and we can see that if we've got this dumbbell here, we've got a person balancing the dumbbell on their fingertip, and the centroid would be the point where force could be applied, where we would have a balance. So it's the point of applied force from gravity, and if we have an object in equilibrium, it's balanced along its centroid. So this object is balanced in a couple of ways. First of all, it's not moving in a linear path. So let's see if I can grab a pen here. So it's not moving in this direction. It's not moving in this direction. It's not moving in this direction or in this direction. So we say that's not happening. But there's also something else that's not happening. It's not rotating either clockwise or counterclockwise. So that's not occurring. If we have an object that's not moving in a linear way, or not translating is the way that would be put, and it's not rotating, that means it's balanced along its centroid. So if the centroid is actually at this location on the dumbbell, then this object is really not in balance, and you can see that it rotates. It's not going to move off to the right or the left generally, but it's going to rotate around this point, which would be the pivot point. Like we talked about in simple machines, there would be essentially a fulcrum at that location. But what is an object's centroid location used for in statics? Theoretical calculations regarding the interaction of forces and members are derived from the centroid location. When we talk about members, members are just parts of a structure. So if we have a truss or a wall, then we would have the individual parts of that wall, such as 2x4 framing. Each 2x4 would be representative of a member. These are derived from the centroid location. So many of the calculations that we do in the future, in very near future, are actually based upon the location of the centroid. So you can determine a centroid location by looking at a cross-section view of a three-dimensional object. So here we've got an I-beam. So if we look at the cross-sectional view of the I-beam, you can see where it gets the name I. And we can actually analyze the centroid based upon that that shape, looking at it basically into the end of it. For symmetrical objects, you have to again think if we're looking into the end of an object, centroid location is determined by the object's line of symmetry. So if we look at something that has a triangular shape, its line of symmetry is going to be straight down the center. This is a equilateral triangle, so that would be just from the apex to the other side. Centroids located on that line of symmetry at a certain location. When we look at an object that is rectangular, we would have a couple of lines of symmetry that we could split it from corner to corner. We could also do from top to bottom and left to right, and in the center where they intersect is going to be where the centroid would be located. Same thing for a circle. We draw a diameter of the circles through the center of the circle here. No matter where we draw from, whenever we have two chords running across, we're going to have them intersect at the centroid in the center. Let's take a look at the centroid location on a square or a rectangle. Centroid of a square or rectangle is located at a distance of 1/2 its height and 1/2 its base. So if we have our base here, and our total distance is from this location to this location, then 1/2 of that, so x here is 1/2 of b, and y here is equal to 1/2 h. And we get these two values, b over 2, or base divided by 2, which is the same thing as 1/2 times base, and h over 2. This symbol is generally the symbol for an average. So we find the base over 2, the height over 2. We draw lines from them to where they meet is going to be the centroid. Centroid of a right triangle is located at a distance of 1/3 its height and 1/3 of its base. So we would have our 1/3 of the base here, or base over 3, 1/3 of the height, which would be height over 3. Centroid is located at a line drawn between those 2 points. The centroid location on a half circle is going to be located at a distance of 4i over 3 pi away from the axis and line of symmetry. So here we've got a 2-inch radius. The radius is actually going to be here. So from this point to this point. So this would be 4 inches all the way across. So this would be 2 inches from here to here. And so 4 times that divided by 3 pi. It's going to be 4 times 2 inches divided by 3 pi, which is 0.849 inches from that center point. So if we move halfway across, or our 2 inches from the edge, either side on that flat edge, we would come up 0.849 inches. Sometimes, though, shapes aren't necessarily quite so obvious as something like a rectangle or a square or a triangle. Sometimes we have much more complex shapes. So to find the centroid on these complex shapes, the calculation is somewhat more involved. So here we've got 3 equations. We'll be using these 3 equations, or actually only 2 of them more than likely. But we can use these to find the centroid location. So let's suppose we have a complex shape like this. Okay, we can first of all, divide the shape into simpler shapes. Okay, and there's more than one way to do this possibly. We're going to divide this into a rectangle, triangle, and then a square. Okay. We will determine a reference axis. Okay, we have our reference axis there, so we've got this corner down here at the origin, and we've got our y-axis here, our x-axis here. In calculating the area of simple shapes, it helps to know your geometric formulas. They are in your equation pages if you need them. The area of the square is just the side squared. So if we call this side and this side is truly a square, they're the same length, and we just multiply side by itself to get an area which is going to be in inches squared or meters squared or centimeters squared. The area of a rectangle is going to be width times height. Area of a circle is pi times r squared, and the area of a triangle is 1/2 its base multiplied by its height. these should be equations that you've had experience with before. So what we want to do, our third step in this, is to calculate the area of each simple shape. Okay, so we've got shape 1 over here. It's our rectangle. So that's going to be, the area of that shape is going to be width times height, and that's going to be 3 inches in width, and you can see here that we've got 3 inches, and 3 inches would be 6 inches in height. So it's going to be 3 times 6 is 18 inches, and that is inches squared for our final unit. Please make sure you're putting units in problems. Our next area is the triangle, area number 2. It's going to be 1/2 base times height. So that's going to be 1/2 3 times 3 inches, which is going to be 4.5 inches squared. And then our square is shape number 3. That's going to be side squared, which is just 3 times 3 would be 9 inches squared. Next, we determined the centroid of each simple shape. And so we've got our areas in the last one. Now we're going to determine our centroid location. So the centroid in shape number 1 is located at the intersection of the lines of symmetry. So we just draw our lines of symmetry, and there we are. Centroid number 2 is located at the intersection of 1/3 its base and 1/3 of its height. So we would find 1/3 of 3, that's going to be 1 inch by 1 inch. Draw lines where they meet or where they intersect is going to be our centroid location. And then for our square, it's going to be at the intersection of the lines of symmetry, which we can do like this. So we have located our centroids just by lines of symmetry. Next, once we've determined our centroid location, we want to determine the distance from each simple shape's centroid to the reference axis x and y. Okay, so for shape number 1, we've got 1.5 inches from the y-axis. So that's actually going to give us an x distance across the x-axis, or horizontal, of 1.5 inches. We've got measuring for the triangle. We've got 4 inches from the y-axis, which is going to be an x horizontal of 4 inches. And for our square at the bottom, we're 4.5 inches. For this one, we would be looking at our vertical. We're 3 inches along the vertical axis. So that's actually going to be, since this is a vertical, this is a y dimension. We've got a y dimension here, which is going to be 4 inches. This one was 3 inches. And then we've got 1.5 inches here. These are inferred from some calculations based on the overall dimensions. So next, we're going to multiply each area's shape, which are given here, 18 inches squared, 4.5 inches squared, and 9 inches squared. So we're multiplying each area's simple shape's area by its distance from the centroid to the reference axis. Okay, so we're going to start by looking at our x's. Okay, so for shape number 1, that's where we are right here. So we're at shape number 1. Our area is 18 inches squared, and we're going to multiply that by our average x distance, which is 1.5 inches. So 18 times 1.5, 27 inches. For shape number 2, we've got an area of 4.5 inches, and we are 4 inches along the x-axis, so that's 4 inches. And then for our third, we have 9 inches squared. And by the way, this was 18 inches squared, so we've got 9 inches squared here. 4.5 inches in the x dimension from this axis to the centroid. So 9 times 4.5 is 40.5 cubic inches. Notice that our unit is inches squared multiplied by inch, which is going to be cubic inches. We repeat this for the y, taking the same areas, but multiplying by our distance along the y. So for shape number 1, we've got 3 inches. 18 times 3, 54 inches cubed. We've got 4.5 inches squared here for let's see, for shape number 2, this says 4 inches. Oh, I'm sorry, 4.5 inches squared as our area, and then times 4 inches at this point is going to give 18 inches cubed. And then we've got an area for this one of 9 square inches times 1.5 here is going to give 13.5 cubic inches. So as you can see, we're developing a rather simple, lots of individually simple calculations, but put into a long series of calculations to find the centroid location on this complex shape. Okay, so now we have our areas, and we have the product of area times distance from the centroid. All right. Step number 7, we sum the products of each simple shape's area and their distances from the centroid axis. So we go back, let's go back a slide here. We've got 27, 18, and 40.5 as this column. So we've got those numbers here, and we're just going to sum them. 27, 18, 40.5, these are all cubic inches, and we get 85.5 cubic inches. We do the same thing for the y, and we end up with 85.5 cubic inches. So we got 85.5 in both cases in this particular problem. Note that this term means to sum of, just add them up. All right. Step number 8, we sum the individual simple shapes areas to determine the total shape area. So at our 18, our 4.5 square inches, and our 9, that gives us 31.5 square inches total. And in step number 9, we divide the summed product of areas and distances by the summed object total area. Okay, so we've got 85.5 cubic inches in both this summation and this summation, and our total object area 31.5 square inches. So we're going to take for x 85.5 cubic inches divided by 31.5 square inches, which is 2.71 inches. Then we're going to do 85.5 cubic inches divided by 31.5, and again it's 2.71. So we go 2.7 inches from the y-axis, 2.7 inches from the x-axis. Draw a line. Centroid is at the intersection point. So does this shape have any lines of symmetry? The answer is actually no. This object is not symmetrical on the two sides of this line, or above and below this line. However, it does have an axis of symmetry from the center of this triangle reference to the corner over here, giving it actually does give it one axis of symmetry. If we had two axes of symmetry, then perhaps we could just connect them, but the line of symmetry will go through this central point either way. All right, an alternative solution would be, and this is the same problem solved in a different way. The previous method added smaller, more manageable shapes to make a more complex part. The alternative method is called the subtractive method. That uses the exact same equations and uses nearly the exact same process, but you start with a bigger and simpler shape and then treat shapes that need to be removed as negative areas. So for instance, here's our original shape, and we determined the reference axis as before. Start with an area that's bigger than what's given. So we've got square equals shape 1, and we're going to remove an area here to get the centroid of the complex shape. Okay, so here's our area that we're removing. So first let's calculate the area of the simple shape. Area of shape number 1 is going to be width times height, which is going to be 6 inches times 6 inches. Okay? And we're assuming here, of course, that we've got an entire square. So this whited out area here has not been removed yet when we do this calculation. So 6 times 6, 36 square inches. The area of shape number 2, note that the area is being, that's since the area is being removed, we're going to call it a negative area. This is shape number 2. This is number 1 is the whole shape. Number 2 is the shape that's being removed. So that's negative of 1/2 base times height, because we're removing it. So that's a negative of 1/2 3 times 3. 1/2 3 times 3 is going to be 4.5, and it is negative square inches. We're going to determine the centroid of each simple shape. So the centroid of number 1 is located on the axis of symmetry of the lines of symmetry. So that would be in the very middle of the square, 3 inches in, 3 inches up. And the centroid location of this area is located at the intersection of 1/3 its base and height. So that's going to be 1/3 base, 1/3 height, so that's an inch on the X and an inch on the Y. So that gives our centroid at this point. Next, we determine the distance from each simple shape centroid to the reference axis. 3 inches here, 5 inches there. Do the same for the Y, 3 inches and 5 inches. Then we're going to multiply each simple shape's area by its distance from the centroid to the reference axis. So the area of shape number 1, which is the square, is 36 square inches, times 3 inches, which is this axis right here. And that's going to give 108 cubic inches. For shape number 2, our triangle, we've got negative 4.5 square inches times 5 inches, which is this line. That's going to give us a negative 22.5 cubic inches. Do the same for the Y, 36 and negative 4.5. We've got 3 inches for the Y and 5 inches for the Y on the triangle. And you get 108 and negative 22.5 again. Next, we sum the products of each simple shape's area and their distances from the centroid to the reference axis. Okay, so these are the answers that we got from the last problem. So we got 108 cubic inches, 22.5 cubic inches. Remember, that is a negative, so we've got 108 minus 22.5 is 85.5. We do the same for the Y, and the numbers happen to be the same. Don't always assume that to be the case. It just is in this problem. 85.5 cubic inches again. We then sum the individual simple shape's area to determine the total simple shape. So we've got 36 square inches for the total area and 4.5 square inches for the triangle. So 36 minus 4.5 is 31.5 inches squared. We then divide the sum product of areas and distances by the summed object total area. That's going to give 85.5 cubic inches divided by 31.5, 85.5 divided by 31.5, and we do that for both X and Y, and we get 2.71 and 2.71, which is what we got before. We get 2.71 and 2.71. Draw a line, find the intersection point. And there's our line of symmetry. So it's a lot to go through. So this is an area where, as you're taking notes, you may have to go back, but it would be a good idea to list the steps without all the sample problems. You can come back and look at the sample problems, but having the algorithm, so to speak, this list of steps that you would go through would be very helpful in solving problems in the future. Right. Some common structural elements that we use in building have some fairly common shapes. And you can see here that we've got a typical beam. And then we also have other structures such as an L shape, C shape, I-beam, or a box. And these tend to be areas, if you think about it, areas. This would be basically, this is derived from this. It's just got a section removed from it. Same thing with the box. The center is removed from it. C or an I-beam is going to be the same way. We still have a rectangular area on the end of this beam, but we have sections removed from it. So we look at an angle shape, an L shape. We can sum those areas in several different ways. For C shapes, we can do the same. So this would be one way that we could sum their areas. This would be another way. This would be another way. And this would be another way. So there are multiple ways that could be done, just depending upon how you decide to divide them up. But we can still find the centroid from those areas. For a box shape, we have, again, multiple ways they could be divided. Notice the difference between these and this one. I-beams. So also more than one way really to divide that up. This is probably the simplest way. And once we found the centroid, if we find the centroid of a structural member, this being some sort of beam, pinned in place, possibly on a hinge or a nail or something at the corners, but it's mounted in place, and we have the cross-sectional area of this beam, which is rectangular. The neutral plane that we have here is an axis of symmetry, okay? Between the top and the bottom. This should be axis of symmetry. Okay, and our centroid, if we look at this as axes of symmetry, our centroid is going to be right in the center of that neutral plane. We would also have to draw an axis of symmetry this way, so that we could look at that one, so that we could find where it was located. But our centroid is here. And what we find is that when we, and this is really looking forward to the next few presentations, when we, for instance, let's suppose that we've got a 2x6 here, and we've got maybe two blocks on either end, and we're standing here in the center of it, or you have a person standing in the middle of it. That's going to cause the beam to bend. There's some sort of load here that's applying a force at this point, and you can see that the beam deforms, or deflects is a better term for it. And what we find is that along this axis of symmetry, we could do the same thing if we turned it over, and it would be along this axis of symmetry instead. So if we turned it so that it was laying on its side instead of upright like this, we find that divides a couple of things that are happening in this beam. Above the axis or above the neutral plane, we've got compression, and the parts of this beam are being pushed together. But on the outer edge, as we apply a force here, this is stretching. So as this bows out on this side, it's stretching, but as everything is coming, they're actually coming closer together and compressing at the top. So we have a couple of things going on this one beam: compression and also tension or stretching. And just another look at it here with tension on the bottom or the convex side of the beam, and compression on the concave side of the beam. And that ends this presentation. Following this presentation, you will have some sample problems